Very important. Great. Okay, Naomi, thank you so much. And I'll let you get started.
All right. Well, I'll share my screen. So hello, everybody. It's a pleasure to be here with all of you today. And thank you, Maureen, for inviting me and my colleague, Rob, to help work with you guys on all this cloud stuff today. So here's my intro slide. It's a little bit more resume style forward than I normally introduce myself at these sorts of events, but I have a background in electrical engineering and computer networking, so I've done a lot of work on computer hardware and how data centers work internally. And these days, I spend most of my time thinking about what people actually do with that hardware and what goes on at the homes of the users of those data centers. And that's why I found myself at the eScience Institute at the University of Washington, where I get to work with seismologists and other geoscientists and all sorts of other scientists on figuring out how to use new computing methodologies to accelerate their work. And so I have a deep background in messing around with computers. I have a very light background in actual scientific inquiry. So I hope you'll all forgive my engineering mindset. But today we are going to be talking about cloud computing. And I am going to be doing a lot of talking up front, but a lot of the work is going to be done halfway through. We're going to switch from talking about the cloud to actually using the cloud. And that is when my colleague, Rob, who is our director of research computing here at eScience, is going to walk us all through some steps that Maureen and her group put together for sort of the most introductory way that you could begin using the cloud. And Yiyu Ni, who I'm sure you all know, is going to be helping us out here. Rob and I have had the good fortune to work with Yiyu at a number of projects before this. So today we're going to be splitting our time up into two main chapters. The first is going to be a lecture style talk about what exactly cloud computing is and how it can be helpful for us to think about it. And we're going to, during that lecture, talk about sort of common workflows for how we might use cloud resources. And we're going to talk a little bit about meta skills, which is how we want to go about applying our energy and our intellect to the cloud when it is effectively an infinite energy sink that you can put a whole lot of time into. So we'll talk a little bit about how to manage that potential to get trapped in just tech skills that you're learning. Then we are going to switch over to a hands-on activity where Rob is going to be walking us through how to create a virtual machine on AWS, which is Amazon's cloud, and install Jupyter on it so that we can begin running Python code and trying notebooks out. But before we get any further into talking about that stuff, I'm actually interested in hearing from all of you. I'm interested in what all of you think the term cloud actually means. And when I say cloud, I get in trouble with this prompt when I work with any sort of geoscientists, because sometimes they get cheeky and they tell me that it's agglomerations of water vapor in the sky that are subject to air currents. But what I actually want to hear is what you think cloud computing means. And I want you to wait and think about it and respond in the general channel of our HPS Slack only when I tell you to. So I'm going to do a countdown in a minute. I'm going to say 3, 2, 1, and then I want you all to post your response to what cloud means in the Slack. So I'll give everyone a minute to think about it, a minute to type, and then I'll tell you to hit the enter button. I want to see a bunch of people typing. There we go. Very good.
I should have responded.
All right. Yep. I think now that responses are beginning to come in, let's hit enter in 3, 2, 1, go. And if you're still typing, then finish your response. Okay, I hear silicon in the sky. Thank you, Rob. Computing available through the web. Servers are located somewhere. A place to host data and perform computation. Derivative products to the user. Large servers that you can access via the internet. Big computing from my couch and laptop. Online sharing workspace. Oh, I like the term sharing here. This is something that I think is sort of invisible about the cloud, but really kind of fundamental to its power, is the ability to share things. Uploading data and using compute. Sophia says it's storage space located in a part of the world which allows not having a big machine at home so that you can do it from your couch, from your laptop. These are great responses, yes. And I'm appreciating the variation in what all of you are bringing up, because in truth, the cloud can really facilitate a lot of things. It is storage, it is big computation, it is sharing. And because of that, it can get a little tricky when we're talking about cloud, making sure we're all on the same page so that we all know what we're talking about. And by the way, please feel free throughout this lecture session to ask questions in the Slack chat, and I'll do my best to catch them and respond to you. This exercise is sort of intended to get everyone a little loosened up so they're willing to interact with the rest of the group, even when we're all sitting here in lecture listening mode. So I want to take a moment to talk about what the exact context of this big computation is, so that we're all on the same page as we begin doing this work together. And this is because I think there are a lot of different things that cloud computing can conjure when you say that term and ask someone to define it for you. So a lot of our first interactions with the cloud are with what we would call consumer cloud services. And the idea with the consumer cloud is that you're working on your laptop and maybe you have too many files that can fit on your laptop, so you put them on an external hard drive. And then you end up with too many external hard drives and you can't figure out which one actually contains the data you care about. And then one of those hard drives dies, and suddenly you have to hope that you made a backup on one of those other external hard drives. And so there are consumer services that we can pay companies for, or that we can have free services that are ad supported or something like that for, that take care of storing files for us. And so this is an example of a consumer service where we don't need to know much about information technology. We don't need to be system administrators, but we can remotely store, as many of you said, our files on a server that is somewhere out there in the world that we don't have to worry about here. And so usually when you talk about cloud things with folks who don't do high performance computing, they're talking about consumer cloud services, things like Google Drive, things like Dropbox. If you've ever used Google Colab, which is a way that you can run Python code sort of in a web browser without needing to run the code directly on your own computer, this is actually an example of a consumer cloud service because it's a very turnkey, immediate system that you can boot up to just run Python code. What we're going to be talking about today, though, is infrastructural cloud. And this is a little bit different in the amount of flexibility and power that it gives us. So the idea with infrastructural cloud is that we might be doing work on our laptops. And once the laptop's not powerful enough, or we run out of battery power, then we might need to take our computing workload and move that to a data center somewhere. Now, traditionally, these data centers would have been either hosted on-prem in our actual institution. So there's a room somewhere in the University of Washington that has these racks and racks of servers that I can log into. Or there would have been a national supercomputing center, like the one down in San Diego, that you log into remotely. And so all that cloud is really introducing here is the notion that there might be a commercial supplier of these servers that we can rent time on or rent resources from. And it's publicly available. Sometimes you'll also hear infrastructural cloud referred to as the public cloud, which is a slightly confusing term because it is a private enterprise running the public cloud. But the idea here is that it's someone taking their internal computational resources and making them available for rent by the public. That's actually where the biggest cloud platform that we are familiar with comes from. Amazon's AWS platform started because Amazon had built these huge internal data centers in the early 2000s to run their e-commerce website, Amazon.com. And they realized that they weren't always using all of those servers, so they could rent some of the underutilized ones out. And as this became a more and more popular service, it quickly became one of Amazon's biggest profit centers. So the question then becomes, once you're using one of these cloud platforms, one of these infrastructural clouds in order to do our science, what are the abstractions that we are using within this cloud? That is to say, on Google Drive, on a consumer cloud service, Google Drive provides us with a word processor. It provides us with spreadsheets and slide decks. It even has a form system where you can request user information. And so today, I think one of the things we're going to be spending a lot of time focusing on is what the equivalent of these services are for infrastructural cloud. Now I'll pause for a second. Might be a good time if the thought juices are flowing to ask any questions that you might have in Slack. I know some of you are pondering interesting things. Marina asks a really interesting question. Why aren't GCP and Azure not at the same level in AWS in terms of market share? That's a really interesting question because I think that it's very multifaceted. I think that there are a lot of reasons why AWS is leading the other two big three in terms of adoption. I think honestly, it's my semi-educated guess is that it's because they were just there so much earlier than Google and Microsoft were to the same market. And because this stuff, as you'll see, takes a little bit of learning to figure out how to use, people are not very excited about migrating to a new platform once they are installed on their current one. So AWS just had a really big lead time in terms of like being available for the public to use. Alex asked why AWS is less user-friendly than Google's cloud platform. Keeping in mind that this meeting is being recorded, thank you, you edited that to say, or so I've heard. I'm inclined to agree with you. But I put a few asterisks there. I have found personally that AWS is harder to use than Google and Azure. Others have sort of have different opinions. I think that ultimately all three cloud platforms, and we'll talk about this during the meta learning part of today's lecture, but all three platforms have their own experiences that are very polished and easy, and the rest of their experience is very rough and difficult to figure out. And so it's ultimately a matter of whatever products and services a given cloud happened to put the effort into making a seamless experience. And one might be better than another in one way or another way. I also suspect that because AWS has such a big lead in the market in front of the other two, that they feel less pressure to make their tools easy to use and easily learnable because there's already a lot of commitment and infrastructure into getting AWS working for people. But you know, people's mileage really does vary here. Ooh. Keeping market competitiveness aside, is it possible to bring all cloud servers working together? Will there be an influence of architecture? That's a really good question. And I'm going to interpret, when you say, will there be an influence of architecture? I'm interpreting that to mean our architecture as scientists. Is that a correct interpretation of your question? Well, keeping market competitiveness aside, there are tools that let you access all of the cloud platforms as one. They are rather experimental right now. And so your experience with them might change from 1 month to the next. I see. And in practice, I think this tends to, I'll defer to Yi, who has actually done work on multiple cloud platforms for seismology. But I think in practice, most of the work that you do will end up being relatively platform agnostic. And this isn't something you should worry about as you're just starting to learn how to use cloud computing. Because in truth, almost all of it is based around Linux and based around Docker. So if you know those things, then they're going to behave more or less the same way. That said, we can get more into detail on this after the lecture if you want to know more about multi-cloud tools, because we work with them a little bit in the experimental work we do at the University of Washington. So moving forward, I want to put forward a few cloud abstractions that we're going to focus on today. And these are kind of the two big ones. So the first one, and this should come as no surprise, is compute. We're here to talk about doing a lot of computation, a lot of number crunching, using computer processors and GPUs, graphics processors, that we might not have access to through our own laptop or through services available from our campus. And in cloud land, compute is almost always referred to as a virtual machine or a VM. So you'll see the term VMs come up a lot, and that's just referring to something that you can literally think of as like an actual computer that you are renting. So it comes with hard drives, it comes with processors, it comes with a network card, it has an operating system on it that you can upgrade and you can log into. And then separate from computation, we want to talk about storage as its own sort of first-class citizen in cloud land, its own thing separate from the computation we do. And that's because there are many different types of storage that can be more or less cost-effective depending on how we're using it. And so in cloud land, storage is often referred to as file stores and object storage, with object storage being the more cloud-centric, more cost-effective way of thinking about storage. And in a moment, we'll talk more about what exactly that means. In addition to compute and storage, there are several other abstractions that it will be useful for us to be aware of as we use cloud infrastructure more and more. But they're grayed out here, they're a little faded, because I think these are a lot less important when you're first beginning to boot this stuff up for the first time. For completion, though, I just want to call them out as existing. So there is a notion of networking, which is to say how the compute and how the storage are connected to each other, and how both of those things are connected to your laptop sitting in a potentially different country entirely. There is this notion of users and security. Who can log into a given virtual machine? Who can create virtual machines? Who can create and delete storage accounts? Who can view items in a storage account, but maybe not delete or create new files? These are all things that fall under the umbrella of the term identity access management. If you ever see an error message about IAM roles, this is referring to effectively user accounts. It's saying that whatever you or your colleague is trying to do is something that they don't have user permission to do. And the process of debugging IAM issues is usually giving people's user accounts progressively more permissions until they are able to do everything that they want to do. There's also this notion of location, which is to say where on the planet the virtual machines and the object storage are literally located. And most of the time, we choose the location that we place things in somewhat arbitrarily. It's important that when you do computation that it's physically close to the data. So if you have a big data set and it's hosted in Central Asia, then you might want to make sure all of your computation is also done in Central Asia. And this appears when we begin creating cloud resources as just a literal drop-down box that says, create this in one place or another place. In practice, the connection speeds between one location and an outside place outside of the cloud data center are kind of negligible. In other words, we could create a virtual machine in Central Asia and then access the virtual machine from South America. And that would be a perfectly usable interface. We don't need to worry about where we are on the planet relative to our data. It's really more a question of where data is relative to the virtual machines that are using it and relative to availability. So sometimes you'll see all of the GPUs in one continent are used up. And so we might need to create virtual machines on another continent where there happen to be some spare availability. And the last abstraction that we want to call out here is this notion of blank as a service. And the idea here is that you can take some time to compose computation and storage into a service like a database or like a server that can run Jupyter notebooks a la Google Colab. But it might save you time and it might save you heartache from trying to debug issues if you can just have the cloud provide you that service already. Say, provide you a database of the format that you don't need to install and set up and configure all of the Linux settings for. And so whenever you see these terms that might look like DAAS, that means database as a service. That's what they're saying is you can pay the cloud some small extra overhead and they will give you a database that you don't have to configure yourself. Or maybe it'll be even cheaper than doing it with plain compute because they can cut corners in certain ways that you won't care about, but that they wouldn't be able to if you were just installing this stuff as software on a Linux computer. So I just want to spend a few more moments just really internalizing this slide. Almost everything we do on the cloud is going to end up being based on virtual machines and based on data stored in a traditional file store, like a network drive, or object storage, which is a little bit more abstract. And these are the main two things that we end up getting charged for. When a virtual machine is turned on, we get charged for the virtual machine. And the storage is usually billed in units of per gigabyte per month. And this is how we estimate the amount of money that we're going to end up spending over time. So just zooming into virtual machines a little bit more, we have a separation of concerns here in terms of the actual hardware that is running our code and what software is installed on the computer. You can think of this diagram as sort of illustrating the hardware and the software side of a machine. So in Cloudland, we refer to the virtual machine hardware as the instance. It's the instance of this virtual machine. And there are different types of instance that have different types of virtual hardware. Some of those instance types may have much more powerful CPUs. Some virtual machine instance types might have a lot more memory. And they all have different prices. So it comes down to us figuring out what our application needs. Do we need to store a lot of data all at once? Do we need to be able to access that data quickly in RAM all at once? And then correlating that to the list of instance types that a cloud provider will make available and choosing effectively one of their model names based on that. There'll be some acronym style name that just indicates, once you know how to read them, that the AWS virtual machine you're creating has a lot of CPU because it needs to crunch a lot of numbers, but maybe not that much memory because it's not storing a huge data set. It's just doing a very intensive computation on a small piece of information. Or maybe you'll find a VM that's the opposite. Lots of memory, not a very powerful CPU. Separately, the virtual machine image is what contains the actual operating system and the software that we're used to using, like Python and like the Python libraries you might install. The image contains our home directory, which ultimately we'll begin putting our code inside of and doing things like setting configuration files. And so a given virtual machine can be of any instance type and have any image on it. So you could take one virtual machine that has an image that you've set up to your liking, turn it off, and then change the instance type without the virtual machine being any wiser. Then when you turn it on again, the image stays the same, but the virtual machine now has a different price point. It costs something different per hour, and it has different hardware capabilities. So sometimes you may need to do a lot of number crunching, and sometimes you may need a lot of memory, but maybe not at the same time. This is a way that you can make your cloud computing very cost effective. And so this is the fundamental building block of anything on the cloud that does work. In general, if you ever actually are running code or doing computation, then there's one of these in the background that's doing the work for you. And they're charged per hour of on time. So when you're done with them, if you turn them off, then you're not being charged for them. But if they are currently turned on, even if they are idle and not doing anything, then you're being charged that flat hourly rate. They're easy to resize, they're easy to duplicate. And because of that, a phrase that I learned from my colleague Rob is to treat them like cattle rather than like pets. You know, if we bought a laptop and we become very connected to it, we might give the laptop a name, we might put stickers on it and begin caring about whether we treat it nicely or not. On the other hand, with virtual machines, if we screw configuration up and we're sufficiently confused, we should feel free to delete the virtual machine, just throw it in the trash and create a new one from scratch. Because ultimately, it's free for us to create and delete virtual machines. The only thing we're charged for is when they are turned on. So getting into this mentality of getting exactly the compute that you need for exactly the amount of time you need, and then deleting it when you're done, is going to be a very, very powerful workflow for us. And in terms of storage, the story is a little bit different, mostly because the storage exists 24/7. We can't quite turn storage off. But I see someone is typing, so if you have a question, I'm very interested to hear it. I always like it in Slack when it says several people are typing. That's how you know that you've reached a point in the conversation that's actually interesting. Maureen suggests that storage should be like 1 petabyte of solid state disk mounted on each instance. This is a funny joke, Maureen. This is, you know, hosting. Sorry?
It's a dream.
It is a dream. I'm sorry that I'm snarky and calling it a joke. I'm calling it a joke because what we're about to talk about is how much storage costs and how to think about it. The truth is, a petabyte of storage can be quite a lot in terms of your budget, but we are getting there. It is getting cheaper. And Abhishek says quantum computing on the way. You can actually rent quantum computers on the cloud. They cost a lot of money. They are of questionable utility for anyone other than a quantum computation researcher, but they are there and it is coming. So if y'all have questions about virtual machines, then definitely finish typing them out and sending them to the Slack chat, and I'll get to them. But I do want to talk about storage here so that we can address this dream of petabytes of solid state disk. So what Maureen is referring to in terms of mounting storage on each instance is this notion of the hard drive connected to a computer. So what she is saying is it would be nice if when we bought a laptop, it came with a petabyte sized hard drive directly connected to it, which would be very accessible, very fast storage, and it would be very plentiful. The problem with this type of storage in the cloud is that this costs the most money per month, because effectively there's no way that the back end of the cloud provider can cut corners on it. It can't share this disk with multiple users at once without us knowing. So what we find is that usually it's a good idea to keep the storage mounted directly onto the virtual machine. That is, keep the storage of the machine type itself relatively small. We're talking less than a terabyte, maybe 512 gigabytes of storage directly connected to a machine. This is what the word mount refers to. The disk is mounted directly onto this machine and no other machine. And in practice, this ends up costing about 16 cents per gigabyte per month. You can see how that doesn't look big, but it can add up as you have more and more virtual machines, each of which requires their own disk. And so the next cheapest alternative is creating some sort of file share. Now, this has a different name on each of the different cloud vendors. On AWS, it's called EFS, Elastic File System. And the idea with a file storage account is that it's sort of like if you have a network drive that the university gives you, it's accessible from any computer you log into. It's not actually physically in the computer, it's hosted somewhere on campus, but it's quite a bit easier for the IT people to maintain and quite a bit cheaper. So in general, if you're working in the terabytes to 100 terabytes size of data storage, or if you need to share the same data between a bunch of different virtual machines, it's a good idea to create an external file store, which will charge you about an order of magnitude less per gigabyte. This ends up being about 6 cents per gig per month. And then finally, the cheapest type of storage is object storage. And this tends to be the most cost-effective way to store data sets on the cloud. But it's a little bit hard to use because instead of mounting it to a computer so that it appears like a folder in your file explorer, it has to be used through an API, sort of like if you imagine uploading and downloading files individually from Google Drive's website. The thing is, this is worthwhile because it ends up being really, really cheap. Of course, these are all crude estimates that don't get into the subtleties here, but it can end up costing as little as about a cent per gigabyte per month. And so you can see how it might be useful to figure out how to adopt object storage into your workflow so that you can really shave down the amount of money you're spending on files while you're not using them. And this is a good time, I think, to address this question that I see popped up. Chen Ray Lin says, think about moving cold data to the cloud, but extract and download small portions to a local computer for analysis. So we're talking about cold data referring to data that you aren't changing or reading very much, but you do want to keep it around. And so the question is, where does it go? Putting it in object storage can be the most cost-effective way to move forward here, because as it's in object storage, usually object storage cloud providers are able to detect when a file is not being read very often, and therefore charge you less to store it as it sort of ages out of being a hot, commonly used file and becomes colder and colder. Oh, Alex, thank you for asking this question. So you ask, are AWS S3 buckets necessarily one of these types? Thank you. Yeah, S3 is object storage. So S3 buckets are AWS's brand name for object storage. And so object storage is a different brand name on all of the major cloud platforms, But effectively on AWS, block storage is called EBS, Elastic Block Storage. File storage is called EFS, Elastic File Share. And then object storage is called S3, which stands for Simple Sharing Service, I think. Something like that. So whenever you hear people talking about S3 buckets, what they're talking about are publicly available buckets full of files that are very cheaply hosted on a cloud platform. Though S3 buckets don't have to be publicly accessible. They can be private as well. Very glad we're bringing all this up. And I'm really glad, Chenrei, that you brought up the idea of moving cloud data to the cold storage in the cloud, but extracting and downloading small portions. Because, this is the kind of thing that you really want to plan out ahead of time. So just to talk a little bit about how we use S3 buckets. And I realize I want to respond to this question in Slack so that you'll all have access to the answer later. S3, good question. S3 is object storage. Thank you, Maureen. Simple storage service. Cool. So the idea with how we might use an S3 bucket full of data is that while we're keeping the data in that bucket, we can't easily access those files from our code as if they were just in a folder on the computer. So we'll download those files to a folder somewhere on our computer. In other words, we'll extract and download the small portion that we want for analysis. We will run our code, and that code will produce some results, which we will upload back to object storage. And then we will delete that portion we extracted once we no longer need it. And so here we are using the storage mounted to the computer, which is the most expensive, to do our actual processing. But for the long-term storage of all of our data set and all of the results of our analysis, we're keeping that in S3. And this is one way to use object storage. As things become more mature, as people have longer to work out workflows for using all these services, there are now Python libraries that do all of this automatically for you. So it makes object storage look almost like a traditional folder full of files. There's a lot to explore out there. But under the hood, this is the difference between object storage and traditional file shares. And so then the question might be, do I want to take all of the data on my computer and upload it to the cloud so that I can keep it for safekeeping and then download it when I'm ready and do the analysis on it? And this is a good first pass at how to house data and do computation on it. The problem that we find is that when labs do this long-term and have very large data sets that they're doing quite a lot of extractions and downloads on, then they can feel like this is sort of expensive. It can begin feeling like they are throwing money away just to keep the files somewhere that are not on their local computers. And the reason for this is because while getting data into the cloud is free, getting data out of the cloud can run about 10 cents a gigabyte. I say it can run about this because even though this is the formal rate quoted by cloud platforms, many institutions have negotiated an egress cost waiver, which means that some amount of the data that you download from the cloud to campus will be free every month. And this is the kind of thing to ask your IT department about, because this is an institution to institution variance. It's kind of hard for us to say as a generality what is free and what is not. There are also open data sets that you can host on the cloud, which you can work out with the provider, with AWS or with Google or Amazon, to not charge egress fees for if it's for the public good as an open data set. But this is not an automatic thing. This is the kind of thing that you have to have a static data set that you get in touch with their program officers about, and then they make decisions about whether to grant that status on your data set. We do have a link to that program here in the slide deck in case you're interested in exploring that later, though. And so what we see is a much more effective way of storing data in the cloud and doing computation is to keep your data in the cloud, but run your Python code on computers in the cloud as well, and use software to provide a user interface through your web browser for running that code, so that it's a whole it's less difficult to get this setup working. And so over time, there have been more and more really nice software packages that make it easy to take code on your computer, put it on a computer in the cloud on a virtual machine, and then have that code do analysis on data also hosted in the cloud. And so if you've ever used Jupyter Hub before, this can be run in this mode where the user interface is on your laptop, but the actual computation is happening on cloud computers. That's what we're going to be learning to do in just a minute. If you or your colleagues use the programming language R, RStudio can also do a similar type of setup where it runs in the cloud, but the user interface is available through your web browser on your computer. One of you asked a spectacular question earlier. Who was that? Was that Abhishek asked, can we use all of the different cloud providers together? SkyPilot is an active project coming out of Berkeley that's currently focused on machine learning, but working to become more general, about allowing you to write the code on your computer using SkyPilot and then use their tool to submit your code to run on different clouds, depending on which one is the cheapest at any given moment. And that's still under very active development right now. So it's a pretty exciting project to take a look at after you do all of this stuff the traditional way and begin getting into more advanced methods. And then Dask is another tool. This one is Python centric, but Dask is a project that aims to allow you to do work on your local computer and then expand to do that work on the cloud once you need more performance, and sort of minimize the amount of work you have to do to move your workflow from your local computer to the cloud computer. And so these are just an example of the tools that people have set up that all assume this underlying model where we do our computation physically close to where the data is stored. That way we avoid having to pay to download the data after it's been put up into the cloud storage. And this is what we're going to be exploring today. And Maureen mentions that today and tomorrow we will be using the SCE-DC open data set, which looks like it is hosted on the cloud without egress charges. Fingers crossed.
It's open data set, so it should be good.
Excellent. Yeah. So that's a very brief sort of whirlwind tour of how we think about the fundamentals of what cloud computing is and how we assemble them. And so before we transition into our hands-on activity, I just want to spend a little bit of time talking about learning to cloud, which, we're already doing. So I think if you haven't noticed this already, there's effectively an infinite amount to learn about infrastructural cloud, because it's effectively asking us to become our own IT department. And so we recommend, Rob and I work with a lot of scientists who are beginning to use this stuff for the first time. And we recommend figuring out how to make sure your focus is always on the science that you want to do, the core scientific methodology that you want to support. And then from that North Star that you're using to navigate, find the minimum subset of tech skills that you need to learn to do your work, and then begin to learn more and dive deeper as you have time. And this is why I'm emphasizing things like going through the tutorial to set Jupyter Hub up today, and then learning to use something like SkyPilot in a month after you have been doing computation using a plain Jupyter notebook for a while now. This can be a really powerful way to learn, I think, any new topic, but it applies very, very heavily here in Cloudland because there's just such a flood of new information that you're going to be exposed to, whether you want to be or not. So say when you're beginning to do things and stuff breaks down because of IAM issues, you're not going to understand the philosophical core of what IAM means and how to avoid this issue in the future. What we need to develop, the skill that we need to get good at, is figuring out how to identify what the error name means and how to fix it, how to Google for this type of issue and the quickest way to get to a resolution so that we can get on with our lives. And of course, this is easier said than done, but I just wanted to call this out as an experience that everybody, even the computationally experienced folks that you work with, see when they're using cloud technology. And the other thing I wanted to talk about briefly is when you start wondering which cloud platform you should use. Because, there's Google, there's Microsoft, there's Amazon, IBM provides their own cloud platform, Oracle provides a cloud platform. There are a bunch of other third-party cloud vendors that provide smaller, more startup-y clouds. But in terms of the big three, or big four if we include IBM, they're effectively all the same in terms of cost and technical capability. That is to say, if you can do something on one of them, then you can definitely do that on the others, and probably for more or less the same cost, at the very least in the same order of magnitude of cost. And so what it really comes down to when you're deciding which platform to use is things like, are there credits or credit programs available for a given platform at a given university? Because maybe you can have some temporary free access to a cloud platform because your university has a negotiated program with that provider. It's important where your colleagues have experience, because you're going to want people that you can ask questions of and cry on their shoulders with. And so if you know people that use AWS, it's a good idea to use AWS, not for any other reason than just you'll have more access to expertise that speaks the same language you do. And then pre-existing documentation and data locality also can affect the choice that we make, which is to say, if you find a guide that tells you how to do something in one cloud, that's a good reason to do something in that cloud. If you have a software package that has a getting started on Google Cloud Platform tutorial, then you might as well choose Google Cloud Platform, even though you could probably run that software on AWS as well. And as Maureen points out, tomorrow we'll be using this data set from Caltech, and it looks like this is hosted on AWS, which is a very good reason for us to use AWS, because we want to place our compute close to where our storage is. If the data set was hosted on Microsoft Azure, we might want to choose Azure instead. And so with all of that said, that's our whirlwind lecture tour of how the cloud works. And it looks like I'm about 20 minutes over my time budget, but I appreciate that my colleagues didn't pull me off the stage with a cane. I think it's time for me to throw the microphone to Rob and get our hands dirty. So I also want to pause and see if anyone has any questions that they wanted to ask before we jump into this tutorial. Thank you for the question, Clara. When is it worth using serverless options, AWS Lambda, compared to processing on EC2/virtual machines? This is a really great question. And before I answer it, I just want to remind everyone of the rabbit hole here. There is a whole field of things you can do in the cloud called serverless computing. This is something that you don't need to learn if you are just beginning to come to terms with and grapple with all the stuff that we just talked about. That said, serverless options are ways of slicing up the time that you spend on a virtual machine. that might be a little bit more fine-grained and cost-effective than charging a flat fee per hour. So the idea with a serverless option, such as AWS Lambda, which is the brand name for AWS serverless, is that instead of having a whole machine that has its own operating system and a user home directory and libraries that you install, you might just have a single Python function that you want to run every time some new DAS data comes in from your remote sensors, say, something like that. And so instead of running a VM 24/7 waiting for that stuff to come in, or turning the machine on once an hour, waiting for it to boot up, downloading the data, then turning the machine off, you might say, ask AWS to run your code that consumes that data and saves it to object storage. Maybe that takes 20 seconds to run, and you only want to rent the machine for the time that that code is actually running. So if you wanted to get very, very fine-grained about when you're being charged for the computation you're doing. In practice, and the most cost-effective time point for this is usually on the much smaller side. So if you have a computation that happens regularly, but at an interval of about well, I guess the interval does not matter. If you have a regular computation, but it takes less than 5 minutes, then it might be worth considering using a serverless option, which might be cheaper. That said, I think that the best way to figure out this kind of thing is to look at the pricing page for AWS Lambda. So if we were to just say AWS Lambda pricing and type it into Google, we find their pricing page. There will be a long description. It's sort of like when you find recipes on a recipe blog and it starts with a really long blog post that gives the story that you don't care about. You just want to find the ingredients to figure out how to make the cookies. So here we can see that they are charging some fractional number of cents for every gigabyte second that your code is running in their cloud. And so what you would do is you would multiply this by how long you knew your function took to run, and then you would multiply that by how many times your function is going to run in a given hour, and you would compare that to how much time you need the virtual machine, the traditional VM, to be on. And based on this, you figure out which is preferable. So you can see how these advanced options are the kinds of thing that when you have time for it, you can look into and see if it begins being more cost effective to do things this way or another way. See, Maureen replied to the question. Maureen says that she is curious about testing this at scale. Yeah, there are a lot of different ways to be cost effective about your cloud computing. EU also has a lot of experience submitting computational jobs that are a little bit larger than what you would use Lambda for. He's used batch computational systems in the cloud, and those are things that you can ask him about. I'm also happy to talk about them, but I think EU and Maureen have more hands-on experience with that than I do.
I think actually,
thanks for the question, Clara.
This is great. These questions come from people who are very close to seismic network operations and cloud storage. So Ellen actually responded from the SCSM that Lambda has memory constraints, and I think it would be great to test how can we push our processing, the type of processing we'll push on Lambda to minimize cost. But it's a little bit more advanced skill that I don't have yet, and so we decided not to talk about that yet. But maybe over the summer we'll be able to do that exercise. Yes, another question about missing links in the Jupyter book page that we put together. It's because we're putting this together as we speak. But for those who have access, I can use the Zoom link as well, Zoom chat for the page. We put together, tested a tutorial to get on the cloud with a simple bit of code And we have some recommendations for Windows, but for those who have issues, we'll be here to help you debug. Naomi, that was awesome. It was a really great presentation. Really helps us give the nice context and big picture of what these things are.
Oh, thank you. Yeah, well, it's time to make that stuff concretely meaningful.
Yes.
Let's see. Rob, do you want to say a word or two about this stuff, or should we go into how should we proceed?
I didn't get to do my. Yeah, I'll start off by kind of introducing this, but can you remind me and tell everybody how the help plan is going to work?
Oh, right. Yeah. So we have, let's see, it seems like we have 40 people in the room right now. If you have questions as you move through this tutorial, I think if you think they are broadly applicable questions, then send them to #general. But if you want to have sort of private individual help with individual helper, we are splitting up who you should contact by your last name. And I'm looking for where those names were. Found it. Okay.
Yeah. Go ahead.
So if your last name starts with an A through H, then private message Marine. If your last name starts between I and P, then message me. And if your last name is between Q and Z, then message EU. And I will send this to the Slack chat.
All right. So shall I start rolling here?
Yes.
Yeah.
Let's do it.
Okay. So hi, I'm Rob, and my background's in glaciology. So, and I've had the good fortune to spend a little time here and there in my career working with seismologists. So this is fun for me. And my day job these days is to support research computing at the University of Washington. So the idea here is to do a hands-on activity with our sort of remaining hour. So congratulations on persevering to this point. And I think as the comment says, I'm going to walk through this activity on a shared screen in more or less moderately slow motion with some narrative. And you're invited to use your AWS access to do the same. And hopefully everything works beautifully and we all get to the end and we've all built some cloud infrastructure for use. And even if it's pretend, you know, it's kind of important to explain why we're doing this. So one of the things that I talk about in discussing the cloud is that when you go onto the cloud from a perspective of somebody who's going to build something, when we say cyber infrastructure, right, and build a working environment, then you get to wear a sign that says you're a builder, and what you're hopefully doing is building that environment for yourself or for your colleagues to work there. So they would be the user, or people who would then come there and use it, or users, of course. And if that's the case, then, and you plan to be a user, then why be a builder? But, you know, I came up with a little rationale for this, which is that if the cloud is new to you and you kind of develop an evolving picture, like somebody just brought up serverless functions, if you kind of build up a little bit of a picture of how that cloud works, then by understanding it, you have a little bit more latitude for creativity. And you can say, what about doing this? Somebody mentioned, you know, what about using all the clouds, and never mind that they're different brands, use them all together, right? That's the kind of thing where you want to be able to have some facility with the cloud so you can start to head down the path of exploring these creative ideas in how you set up your environment. So the way this works, and if you've already started, that's great. But the way this works is I'll share my screen. Screen two, let's try that. Screen sharing. Okay, how does that look? Can you see AWS 101 there? Did I
Yes.
share the right thing? Okay, great. So the way that this works is, as per Naomi's recipe metaphor, is there's a little bit of text up at the top, and then it comes to this section called, well, first of all, it says before the 2023 workshop. So if you've had a chance to do that, that's great. And then choosing a region, I'll explain that, and then launching an instance, and we go from there. But as we go from there, there's these little sections, these boxes, which have, copy features over on the very far right side. So you can copy the text and then paste it into a terminal and run it. And so that's a little bit magic, especially when it gets down here to installing software. So we may pause periodically, and somebody, either me or maybe Naomi, will jump in and explain what some of these magic words and phrases mean with some exposition. One thing I want to mention in advance is we're going to be connecting to a machine in the Amazon cloud. That machine is sometimes called a virtual machine. Sometimes it's called an instance, and the Amazon brand name for it is EC2, which stands for Elastic Cloud Compute, something like that. So you have all these synonyms, and it's sort of tough to keep them straight, but I'm going to mostly use virtual machine. We're going to be setting up a virtual machine on the cloud and then installing some software. That's the game plan. And in order to do that, the connection is a network protocol called SSH, for secure shell. So the initial part that I wanted to start up here was choosing a region, and that's the beginning of my bit about learning cloud, is that the cloud providers have data centers. It's not actually up in the air. The computers are sitting on the ground in a data center. And these are divided into regions. So you can choose the region on the Amazon console. It's up at the upper, you see, I'm switching my screen to the Amazon console. I'm on some random page. This happens to be Lambda functions, but you can notice up here at the very upper right, it says Oregon, and that's the region that I've chosen. If I click on that, it turns into a menu, and you can choose a region closer to where you happen to be. And that's going to maybe cut down your network speed if you're talking back and forth with it. So that's the whole point of the region. I'll stay in Oregon, and I'll go back to Magic Spells, the high performance seismology website with our recipe. And this, by the way, is going to persist after today. So you'll be able to come back and redo this stuff as many times as you like to sort of solidify the process. I'm going to move on to launching an instance. And in this case, we have choose a default instance operating system, and we're going to use Amazon Linux. And as we go through this, there's going to be some references to what's called a key pair file. And that's a file that has a bunch of random text in it that allows you to sort of authenticate. And the normal or traditional file format has a file extension .pem. However, if you happen to be using a Windows machine and you're going to use the PuTTY application, it uses a variant of that file, and it has a slightly different file extension. It's .ppk. And if you're familiar with this, then it'll be old hat. But the point is that we're going to generate that key pair file in the process of starting up the virtual machine. So in generating it, if you're going to be using PuTTY, you want to generate the PPK. Otherwise, you want to use the PEM file. Okay, so I'm just going to go over here. Let's see. I don't see panic in either Naomi or Maureen's eyes, so
No, it's good.
so far so good.
Yes, the login URL, if we wanted to get to it, is on the top of that page.
Oh, let me go back to that.
And it's an account that is created from a cloud bank account for Scoped. So if you click on that link, it will prompt you to logging in under this account that we created for this workshop. And perfect. And those who have had gotten some username authentication and reset their password, they should be able to log in on the console. And this is when things start. I'm waiting for the messages.
Yeah. Yeah, and I'm infinitely interruptible. So if somebody wants to grab the mic or whatever, please do.
Thank you, and sorry for the interruption.
Yeah, no problem. Let's see. Okay,
Yeah, so
so
everyone can
right. So taking the login as read, I'm going to show you how to find the launching an instance business. So the dashboard, where I mentioned I'm in this sort of Lambda space here, it always has this search bar up at the top. And I said EC2 is the brand name for a virtual machine. So if I type EC2 there, it gives me the option in the search result of EC2. So I'm going to click on that. So that takes me from anywhere in the Amazon console to the EC2 dashboard. And it's listing out a bunch of information here. I'm trying to minimize the amount of clutter that I give you. So I'm just going to focus on this orangey button here that says launch instance. So launch instance, that means launch a virtual machine, launch an EC2. So I'm going to click on that. And it's going to take me to a wizard kind of page where I get to make a lot of menu choices to set up my machine. And the first thing I need to do is name my machine. So I'm going to name my machine with my name. So Rob Fatland _ seismic. That's going to be my machine name. So don't use that name. And then I'm just going to keep on scrolling down through this page, observing a couple of things that I pick out. Most of the stuff that we enter here is default. So it's already selected Amazon Linux, and I'm clicking on that, nothing changes. That's actually what we want to use. Let's see, free tier eligible. Okay, whatever that means. Everything here is fine. I'm going to keep scrolling down until we get to instance type. And it says here t2.micro. So t2.micro is just a flavor of virtual machine. And that's a small, it's like a Raspberry Pi. And it's really cheap. It just costs, you know, pennies per hour or a penny per hour or something like that. And it's freely available, so that's great. So now we get down to key pair login, and this part here is what I was referring to. We're going to either select an existing key pair, but I don't have one, so I'm going to create a new one. So I'm coming over to this hypertext and clicking on that, and that's going to give me a little digression for a moment. Okay, enter key pair name. So okay, so let's see. I see there are a couple of questions, but I think those are being handled. So I'm going to call this my name again. Oops, don't know how to spell my name. Key pair. Okay, so there, I've given my key pair name. RSA is fine, and then it says here private key file format, and I'm using .pem, but you can also use .ppk if you're going to be using PuTTY. So that's where you select that. I'm going to create this key pair. Sorry, or Windows, yeah, right. So I'm going to select that key pair file, and it brings up a saver. And I'm going to save this to my downloads folder. And I think it's worth mentioning really quickly that I'm going to be doing everything on my own machine using a bash shell, a one-again shell. But you can actually start running a shell inside the console. And it creates some separate issues that we don't want to try and explain today. So I'm just going to point out how you would get to that thing, and then I'll turn it off again. So up here at the upper right, there's a series of little menu items, including a little greater than underscore. And when I hover over it, it says Cloud Shell. And when I click on it, it creates this shell box in the bottom part of my screen. And I can even grab onto the control and make it bigger or smaller. And if that's kind of small print, all it is turning on a shell. And I can say ls, and there's nothing here. And I can edit a file called a.c. And I can save it probably. I can cat that file a.c. So there it is. Okay, so I've basically demonstrated that there's a little Linux machine just kind of waiting for our use. It's not something where we live and work and breathe, but it is useful if you need a terminal and you don't want to use your own computer's terminal. So I'm going to delete this by just hitting the X on the upper corner there. And on we go. Okay, so network settings. Again, there's nothing much to do here. Everything is fine. And it mentions something called a security group. And I believe that the instructions have us select an existing one, which is the default. So if I click on select existing and click on default, and we've done that. And the security group is essentially a cloud construct. It's like a logical entity that has rules about how we can behave. And anything that's inside of that security group or that adheres to that security group must follow those rules. And in particular, it will have rules about inbound and outbound network traffic. Okay, configure storage. This is, again, nothing to do here. There's only one last little detail to take care of, which is under advanced details. The instructions say request spot instances. And even though we're only spending a penny an hour, it's good to note that there's a way of reducing your spend even further by selecting spot instances. And these are instances that have a complicated backstory, but the bottom line is that, don't need to keep scrolling here, I'm sorry. The bottom line is that they can be taken away from you at a moment's notice, but this happens only occasionally, and so you just have to be ready for that to happen. Okay, so I'm going to click on the orange button that says launch instance, and we'll see how it goes. Success. Okay, fantastic. So we've successfully launched a virtual machine on the Amazon cloud. And if I click on this hypertext, it will take me to the information for that virtual machine. And our next step will be simply to log into that virtual machine. And again, it's a Raspberry Pi, so it doesn't really take very long. If you've got a really powerful machine, it might take a minute or so. And something I want to point out is that I have a scroll bar here that allows me to scroll over and find the IP address for this virtual machine, which is 35.89, etc. So back to our recipe page. Okay, so now we need to connect to our machine, log into it, and we're going to do this using that PEM file, that PEM file. But up here, there's a, where'd it go? Oh, sorry, it's right in front of me. There's a chmod command, which changes the permissions on that file. So I'm going to go to my local shell. Here I am. I'm going to copy from my downloads folder that key pair that I just created to here. And I'm going to chmod 400, that key pair file. And now it's usable by the SSH command. So I will say SSH-I, and then I give the -I the argument of my key pair file. And then I need to give a username and an @ sign and the IP address. So EC2 user @ And now I need to remind myself, sorry, what the IP address is. At 35.89.253.56. I claim this is everything I need. You know. Something has gone awry. Resource temporarily unavailable. I wonder if that means that my spot instance has been taken away.
I think it's still initializing, no? Maybe on refreshing the,
That could very well be. It's just maybe it takes a little bit longer to be available. Could be a good time for a coffee.
some of you could not start the Cloud Shell. Actually, I never used it, so it's a good practice.
Yeah, it seems like there is an IAM permission that lets people use Cloud Shell or not. So we might have to grant that to you guys. That might be hard to do in the moment. But ultimately, you should be able to run these commands either from the terminal app on your Mac, if you're on a Macintosh, or by using PuTTY to do remote login and skipping these commands if you are on a Windows PC.
Yeah, this is the kind of shenanigans I ran into when I first ran through this. But it says that the instance is running. It's very peculiar that I keep getting the message. At EC2 is missing. Oh yeah, there's a longer version of the IP address, so I kind of did a shorthand version of it. And you're right, I could try and use the longer version of that address. Let me bring up the instructions again.
So I just added a permission on the IAM supergroup, user group. So I'd like some of you to try connecting to the Cloud Shell again and test it out.
Let's try exactly what was suggested. Didn't like that.
Could you try copying the DNS value in the table if you go back to the EC2 page? Try copying the public IPv4 DNS, using that instead of the IP address.
Good idea. Yeah, so one of the folks on the call says, how do we know my own EC2 user at? So the EC2 user is the same for everyone. And then EC2.IP address, the thing that changes for each individual person doing this is the IP address. And the IP address you find by going to the console page for your particular instance. Mine is given here by this name, and by scrolling across, and that is where the address is. So I tried first to use the abbreviated version of the address, this thing here, and then I tried using this, and just not giving me any fun at all. So actually, if somebody is successfully logging in, that would be great to hear.
So I don't see as many instances as participants, so I'd like to get could you please update on where you're stuck and how we can help you?
Okay, so
And then-
Tara and Felix are both in good shape. So that's good. I would rather everybody else gets there than me.
I'd like to say the homework for my class this past week was to get to do this within 4.5 minutes.
Uh-huh.
And I think they managed after doing it again and again and again and again.
All right, just for fun, I'm just going to run through this really quickly.
Cattle, not pets, Rob.
That's right. Blow it away and start over again.
Can I ask about the Cloud Shell? When you get on it, where are you?
Mm-hmm. You're on the cloud. It's a persistent memory, so it's mounted in some kind of an environment. I'm not going to use the container word because I'm never sure if it's a container or not, but it's definitely a computing environment that behaves like a virtual machine, and it evaporates, but it remembers anything you did there.
Mm.
And it's sitting on the cloud, so you can connect to anything on the web.
So you would have to upload your PM file to then log in on that instance?
When you go to the Cloud Shell, because you're already authenticated into the console, there's no PEM file. But I think what you're saying is you need to get your PEM file to the Cloud Shell, and that's absolutely true. It has an upload utility, so you just click on, like actions, and it gives you an upload, and so you can upload that PEM file to the Cloud Shell.
I'm glad this is recorded.
Here, it's everything. Gotta be careful. Okay, so what I did was, per Naomi's reminder, I threw away cow number 1 and started cow number 2. And in other words, I created a second virtual machine called R2, and I did everything pretty much the same. And now at this time, it's giving me a login. So hooray, I'm in. And now we're going to very quickly return to the instructions. And having logged in, I'm going to grab this get in Docker install code block here. So I'm going to copy that, and I'm going to bring up my shell. And I'm going to run all the stuff. So this is essentially 6 commands that are going to configure my cloud virtual machine to know all about Docker and to know about Git and to have an Anaconda Python environment. I think that's the basics of what it's doing. Yep, so if I type the command conda, it knows what that is. So that's a good sign. Let's find out what version of Python we're running. Ooh, we're running Python 3.10. Okay, so that was magic spell number 1. And magic spell number 2 here is, now you can install your software, clone your repository, install your environment, run your scripts. Here's the example. So I'm going to, again, copy this. And it's getting the SeisCloud GitHub repository and making a clone of it. So I've copied this block of text. Now I'm going to paste it and run it. And if you happen to be familiar, sorry, go ahead, please.
Sorry, I was just going to say, this is where you can make your own, bring your own repository. And the point of going so raw in setting it up is we think that as seismologists, we like to control our software environment and we like to make our own codes. And so we're demonstrating the steps for you to create it from scratch. But we think that, if you have your repository and your conda set up and your requirements well organized, they should work. Thank you.
Yes, excellent. And this is using the recommended course of action is to create a customized environment. So this 4th command, conda activate SeisCloud, is saying, well, I have a conda environment called SeisCloud, and I'm going to turn that on. And within that environment, I'm going to install all of the libraries and packages listed in the requirements.txt file. Okay, so this is also run successfully. And the next section here is download/upload to your EC2 instance. And I'm not going to actually do that, but this is how to transfer files back and forth from your own local machine, for example, or some other server to the EC2 instance that we're setting up. So, and by the way, the very first 3 letters here are SCP. That's secure copy. It's the sort of cousin or adjoint function to SSH. And then there's a Windows variant here, PSCP, which is maybe the power. No, I don't know. I better not say anything, get it wrong. Okay, and then Jupyter Notebook. We can set up a Jupyter Notebook. There are basically 3 steps to this. The first step is to type this Jupyter Notebook start command. And the magic of the IP 0000 means no matter where somebody's coming from, if they want to connect to this Jupyter Notebook, then that's okay by us. So I'm going to copy that. And I'm going to bring up my paste and run it. If you've done this before, if you started running a Jupyter Notebook, you know that there is a long token string. In this case, it starts BB78C, etc. It's about that long. And that's used to authenticate into the Jupyter Notebook. So in order for this to work, I'm going to need another shell. And in that shell, I'm going to set up my own computer to pretend that its local host is actually connected to the cloud computer. So that's the command. Oop. Once again, I'm going to need to go grab that IP address from my virtual machine. Okay, push me up. Oh dear, that's not good. Oh, I spelled it wrong. Spelled the name of the key pair file wrong.
This is a little bit of a tricky step, so we can repeat that step for those who are not making it.
Yes, I'll bring the instructions back up. And the instructions that I was just executing here is this tricky one here, SSH-I, and instead of, in quotes, the user.pem, I'm gonna actually put the name of my PEM key pair file. And then the user is going to be, the username we've been using is EC2-user, all lowercase, @ and then once again, the IP address of the machine, the virtual machine on the cloud. And then the rest is just verbatim, -L, etc. Localhosts and mates and stuff. So EC2-user, that's substituted for this. The key pair is substituted, and then public IP address is once again what you find on the AWS console under public IPv4 DNS. And when all that is working, the wind is with us. You can type in localhost 8888, and it thinks I'm trying to do a Google search. I don't know why. Huh. If I enter it again, it magically this time actually goes out on the internet and tries to connect to localhost. So here comes a terrible explanation. You ready? I'm typing in localhost :8888, which means go to my own computer, that's localhost, and try and connect to port 8888. But the previous command that I entered said, no, rewire localhost 8888 to this cloud computer. So I'm redirecting myself. It's like I'm my own traffic director and connecting to the cloud computer, which at the moment is running a Jupyter Notebook server. And that's why it says Jupyter here. It's microscopic font, so I'm going to bump that up so that you can see it. And it's prompting me for a login token. Okay, so fine. I'll go back to my my bash shell. And here's my token. So I'm going to copy, oops. I'm going to try and copy this token. And paste it in here. And log in. And behold. There you go, Maureen, you did it. I'm all set with a Jupyter environment on the cloud that I've built in these last few minutes. And it even features a IPython notebook that I can click on.
Easy, right?
That was so easy. I'm just relaxed. And look, oh, it even comes with some data.
Yeah, I forgot to clear the output. Yeah.
Yeah, but that's okay. It's simply that way. So here we go. We have a working Jupyter notebook with seismic code, and oh look, just randomly here, it refers to s3.bucket. So there's some object storage that's involved in the process here, and so forth. Okay, so Happy days.
And so it would be great if everybody could get to that stage, or run the or be able to run the Python scripts that is equivalent to the notebook.
Yeah, and I'm thinking that that would be a good stopping point for my narrative. We could continue onwards to the next part, which is I can mention what virtual image concept is, and I'll mention the Docker concept here. But then let's stop doing the sort of trying to reenact everything. Okay, so I'm going to slowly scroll back up to save the virtual image. What I'd like to tell you is that on the cloud, we can request a virtual machine and we can treat it like our very own pet cow. No, we can treat it like an environment that we configure and work on, right? But what happens if we decide to accidentally delete that environment? Then all of our hard work is gone. Well, that's why you want to connect your code base to a software control repository like GitHub, and why you want to have your data sitting in object storage, which is independent of virtual machines, so that if something happens to the virtual machine, then your object storage is somewhere else and it's fine. But here's another nice feature of the cloud. You can create an image from a virtual machine. And an image you can think of as a file. It's just a bunch of bits, but those bits capture exactly the state of the virtual machine. When you take that snapshot of the virtual machine and create the image is stored away, again, in some memory somewhere far away from the virtual machine. You can blow the virtual machine away. We got a really tiny one called a T2 micro, and we could make the image, again, that's stored somewhere else, blow away the T2 micro, it's gone, it's terminated in the language of Amazon. And then we could go and get a more powerful machine and reinflate that image back on the new machine. So it'll have the same operating system, the same files, everything will still be there, but it'll be on a much more powerful machine. So you could do some heavy computation on it. And if your goal for the day is just to do some editing of files and not do any heavy computation, you could restart a virtual machine image on a really lightweight one. So you have this sort of freedom or latitude about what kind of horsepower you want to put behind the image that you've saved. So that's the purpose of this particular section, is saving the virtual image of the virtual machine. And then the last bit here, I'll invite Naomi to come in and explain. Naomi, you want to grab the mic and run through this whole Docker concept?
I do. I'm just typing out a message to help someone debug something, though. Just give me 1 minute.
Okay. While we're waiting, this last section here, terminating an instance is what I was talking about blowing away a virtual machine. And it's important to understand the distinction, as the text here indicates, between stopping and terminating a virtual machine. If you stop it, it's like you turn it off, and you can come back tomorrow and turn it back on again, or come back on Monday and turn it back on again. And when it's stopped, you are not paying to use it. But it's still there and it still remembers everything. If you terminate it, however, that's much more severe. Everything that was there is gone and you can't get it back. Maureen has mentioned a 3-minute record.
What am I talking
about? Take it, Naomi. Oh, you're going to explain in 18 minutes or less? No, let's just say, I'll leave it to you what the time frame is, but explain containerization and Docker.
Oh, okay.
We already had a lecture on containerization this morning, so you can actually assume that a lot of people know what the container should be about and would be interested in deploying it to save you an hour.
Okay, yeah, that's good context. Thank you, Maureen. Yeah. So you can run Docker on a virtual machine using the commands that the HPS folks put into this guide. So at its simplest, you can run Docker on a virtual machine the same way that you would run it on a local computer, which is to say Docker is an application that you make sure is installed on this remote Linux machine. And once it's installed, you can then pull containers onto it and run them. This is a very common way of deploying complex workflows onto a virtual machine. Say if you have a bunch of different pieces of software that all need to be running and they're really touchy getting them to run, you might put things into Docker containers and then you know that you can run them the same when you're developing them on your local laptop and then when you move them into the cloud. A different way that you can use Docker containers that we won't go over today begins getting into this serverless territory where you might say, I want the computation that my Docker container does to be the only thing I pay for. I don't want to have a big virtual machine with lots of GPUs attached to it that I have to turn on and then manually go in and install Docker and run the container and do all this stuff. In order to facilitate that, most clouds have some sort of container service where you can tell them the name of a container that you have published publicly, or you can upload a container image that you want to keep private, and it will run this container and only charge you for the amount of time that the container is actually running. And unlike the AWS Lambda pricing that we looked at before, where it was like a tiny fraction of a cent, there are a few different pricing plans for running Docker containers on their own without a virtual machine, but it usually is about the same cost as running it on a VM. It's just a matter of not having to do all the setup involved with it. The final place that Docker might come up when we're talking about deploying things in the cloud is when we want to, say, do a HPC style job submission system. So if we've ever used high performance computing clusters, either remotely or at our own home institution, then we might have interacted with these things called schedulers, where you describe the code that you want to run and the environment that it needs, and then you submit it using something like Slurm is a common job scheduler. Then your code gets run and the results get shipped back to you. There are similar types of services on all of the major cloud platforms. They all have their own brand name, and many of them accept Docker containers as sort of the easiest way to package a job up. So these are places that we might see Docker show up in the cloud. In practice, the way I use Docker the most in my day-to-day life is by just running it the way that we see in this tutorial here. Though I have worked with scientists who use it to do sort of an HPC style job submission thing before. Is that a good spiel, Maureen? Do you think that covers it?
Yes, we've talked about, this is great. Yeah, getting on that should help everybody be able to run it from there.
Cool.
I was a little bit distracted because you probably have memory crashing for some of you. And that's because the T2 micro might be too small. I just could have wrote the script with an hour of data or more. And so you may want to either reduce the number of the window length or start a T2 large instance. But I'd be curious if those who have gone already, as we just talked, Naomi talked a lot about how to deal with these containers, and you've learned this morning how to make one. And so can you please try to pull the Docker image and launch it from there, from your terminal, or Cloud Shell for those who have refreshed and relogged in and are able to do it. And then the other thing I wanted to note is you can do this locally. This is, that's the advantage of having these cleaned up environments, is you can run it on EC2 or on your own. It should work the same, especially if you use the Docker version. And the other thing that matters maybe for this cohort is because we're using the data that's hosted by the SCSN on AWS, and it's free to download, and nobody's that I know, I'm not paying for storage. So the reason why it can work is you can actually query the data from the web services and from S3 for the same station. Just one is downloading from the servers at the SCSN network, and the other one is downloading from the S3 bucket that the SCSN has supported. You may notice less difference in download time if you do that locally, but you would notice a drastic difference in download time if you do it from EC2. This is the advantage of working there. However, I have noticed that some of you are in different regions, and if you would like to be close to data, as we have discussed with Naomi and Rob over this past hour or two, you may want to choose a region where the data is. And the data for the SCEDC data is on the US West 2 region in Oregon. And so when I log in, I just always put myself in that region where the data is. Happens that there's also DAS data there. So it's practical, matter of fact, most of the seismological data that you can play with on AWS is in that region. I'm challenging if you can actually run the Docker and start the Jupyter notebook from there.
Did you want me to try and do that? Or are you challenging the participants?
The audience and you? Sorry, I didn't put the, I'm tired. This is the French coming out. I'm not completing sentences in the English way. If we want to test, we can go ahead. Rob can go ahead. Everybody can do it. I had to log in and out multiple times because of the accounts management. Although it doesn't matter, I should still be logged in on my SSH. You may see as you pull the image, see how it's a big image actually. I think we were pretty lazy in building up the Docker file. And you see that you waited time when you pulled it, and you're paying for it. I mean, we are, but the bottom line is we are dealing with a large somewhat large image. And this morning, Ian, we're talking about minimizing the size. And as you're spending time pulling your image, you're spending money. This is where I was trying to bring up the discussion that minimizing image size would reduce cost on the cloud. It is for this step. In part because you open your computer, you're gonna do one process now, so it doesn't really matter. It's a toy exercise. But hopefully in a couple of weeks, we'll have a lecture on batch deployments, and you will see that the advantage of the cloud is this horizontal scaling of using a lot of these virtual machines. And so if you pull that image on 1,000 of these, you're spending 1,000 times how long it takes to pull the image. And therefore you're paying 1,000 times the cost of that download. And it matters, maybe we'll have some of that discussion tomorrow when we do a machine learning workflow that, for instance, GPU images that require CUDA are a lot bigger than the CPU only images. And there's been examples on Azure that you and Zoe Cross show that you can actually do machine learning using CPU, and it's cheaper and as efficient if you do a small container.
Meanwhile, back in the world of tactics, I think it failed because I forgot to stop my Jupyter notebook server that was running earlier. I have to do this over again. Now it's working.
Can you guys give thumbs up maybe on Slack on whether or not, or mention if you have managed to open the notebook?
Well, I'm not going to win this contest because it's not working for me.
I think you have a very nice live demo of what it is like.
That's right. Now for accurate experience reproduction. Okay, so that's fine.
Yeah, when I need to work on cloud infrastructure, that usually ends up being the thing that I'm doing that day.
In Slack, could you tell us if you have computed or calculated the time it takes to download from web services versus the time it took from the S3 bucket? This will help me verify if you've done it. So I'll put mine. And then I have to bike up the hill, so I'm gonna have to leave sharp 5.
A lot of really great debugging questions happening in #general here. This is, I think, one of the most productive cloud tutorials that I've ever been to. You guys are amazing.
Well, you led us well. Well, Naomi also an expert in the Windows login, I can tell.
I force myself to use a Windows machine at work so that I can help folks when they run into problems with it.
Appreciate what your selfishness is not there. You're like really giving yourself all the hardship to help others. That's really nice. Selflessness, I think that's what they say.
That's the electrical engineer in me. I just like experiencing pain, you know.
Can't say that at UW and Microsoft helping us out.
It's an interesting comment from Melanie to factor of 10 in speed from web services versus AWS.
And you're doing still a really good backend server, SCS, and we've hammered these and it's still pretty good. But this is great to motivate. Faster than Iris, let me say. Okay, I gotta go swim class. And maybe Rob, would you like to be host? I know it's the end of the practice session. So I could leave you more time. I know it's the end of the business day. We can go back to it tomorrow. We'll practice more in AWS. So what we could do is work offline at this point. And thank Naomi and Rob for really giving us a really nice presentation overview of what the cloud is. As very attractive as it is, and you know, hard to boot sometimes, but very efficient in data processing once we get there. So thank you all for your patience. We'll do more practicing tomorrow morning. Sounds good?
All right, that sounds good. Thanks, Maureen.
Thank you, everyone.